In today's lesson, we're going to look at cloud formation and how humidity and lapse rates affect cloud formation. This is part of the OCR A-level spec where you need to know about processes in the water cycle, but specifically formation of clouds. I'm going to go through some basics about atmospheric pressure and what happens to air before we kind of go into the main stuff. So on the most basic level, if the sun heats up the ground, that will, through conduction, actually kind of heat the air up around it. So I've drawn here a parcel of air, and because the ground has been heated up, that is in contact with the ground and it's heated up, it's the air around it. When we get air being heated up, as you would have learned at GCSE, we get that parcel of air will actually rise vertically and expand. And this is a process we call convection. You get convection in lots of other things, but here we're thinking about a parcel of air being heated up, rising vertically through the air and expanding. And if that parcel of air is warmer than the surrounding air, so the surrounding air here is 10 degrees and that parcel is 20 degrees C, it will continue to rise. So that's the basics of what happens when we heat up parcels of air through this process of convection, and what will happen to the air in relation to the temperatures around it. So we just talked about how air rises and expands, and I'm going to talk a little bit more in depth about that in a process called adiabatic expansion. So here's my parcel of air. I've got molecules, slash particles in there that are kind of hitting each other. They haven't got a lot of space at the moment. And so they're kind of colliding, and that's creating energy and passing on heat between them. And because they're crammed in, we could say it's a parcel that's got air pressure that is high. And so when there's high pressure, like I said, they hit each other frequently. There's lots of kinetic energy, heat being transferred, because they haven't got much space. If we cause that parcel to rise, if we heat it up and rise, what's going to happen is it's going to expand. It's going to expand, and that means the pressure is actually going to go down. What that actually means is all those particles and molecules that were in there are actually not colliding as much. So they're not having as much energy, and they're not hitting each other as much. That means that kind of transfer of heat is not going to be happening. So what happens is when an air parcel rises and expands, first of all, the pressure goes down, but then that also means the temperature goes down. And this is what we call adiabatic expansion or adiabatic cooling. The basic idea is that as an air parcel rises, it expands, the pressure drops, and the temperature goes down. We're going to come back to adiabatic expansion and cooling. It's important for the condensation process, but we also need to learn about humidity. Humidity is the amount of water vapour that's in an area. So we're talking about parcels. It's the amount of water vapour that we might find in a parcel. We're talking about humidity. And this is very important for how we kind of understand the forming of clouds. We need to know about how much water vapour is in it, because when it gets to a certain point, that will be saturated and condense into clouds. I'm going to talk about absolute humidity first. So this is the total amount of water vapour that one parcel of air can hold. So I've got my parcel of air here, and when we measure it, just so we know that the right kind of figures to it, we can talk of grams of moisture per cubic metre of air. So that's G/cubed metres. Here's my parcel of air. It's 30 degrees in this parcel of air, and that means the max amount of water vapour this could hold is 30 grams of moisture in that cubic metre of air. If I filled that completely with water vapour, if the 30 grams of water vapour filled it, that means it would become saturated, and when it's saturated, that's when we get condensation occurring, and that's how we get that process of clouds forming. Here's another example. The temperature inside this parcel is actually 0 degrees, so it only takes 5 grams of moisture to actually fill up and saturate that parcel of air. So we can learn two things from this in terms of absolute humidity. The warmer the air, the more water vapor it can hold. So if I'm talking about tropical rainforest, the air rising in parcels there is going to be able to hold a lot of water. But also in that colder air, on this right one, it will take less water vapor to become saturated. So if we look in the UK, the air is colder than the tropics, and that means it will take less maximum water vapor to actually saturate that air than if it was a tropical air. This is that idea of absolute humidity, is the total amount of water vapor that a parcel can hold. We now need to look at relative humidity. So again, I'm talking about this parcel of air that's 30 degrees, it can hold 30 grams, but relative humidity means the amount of water vapor as a percentage of what that parcel of air can hold. So what I mean by that is this parcel of air might not have 30 grams in it. It might only have half of that. And so if it only had 15 grams in it at the time, we would then say the relative humidity would be 50%. So we could have potentially be able to store much more, but at the moment it's only storing 50% of what it could store. So that's relative humidity. It's like saying I could do 5 preps tonight, but I've only done 2 preps, and therefore I'm only working at under 50% of what I actually could do. What we do need to know, though, is to become saturated, it needs to reach 100% relative humidity. When it's 100%, when it's reached that 30 grams for this particular parcel, it will become saturated and condense. Years of humidity to cloud formation. So in the lower atmosphere, if I go up in height, I actually see the temperature go down. You might have had this similar experience. If you go up a mountain, as you get higher up the mountain, the actual temperature goes down. So there is this idea, there's this base rate at which if I go up through the lower atmosphere, the temperature will go down. It's known as the environmental lapse rate. That means for every 1,000 meters I go up, the temperature of the air will go down by 6.5 degrees Celsius. So if the temperature is 13 degrees at sea level, if I go up 1,000 meters, it's going to be 6.5 degrees C. If I go up another 1,000, it's going to be 0, and then minus 6.5 degrees C by the time I reach 3,000 meters. However, I need to now think about this in terms of parcels of air and whether the parcel of air is dry or saturated, because these parcels cool at different rates. I put on here the dew point. The dew point is basically the point at which the parcel of air is saturated, and that means it started to condense, otherwise known as the condensation point. So that will depend on the parcel, but I've put it here for this example. So if I look at the dry adiabatic lapse rate, that's the parcels of air that we would call dry. What I mean by that is they haven't yet reached that 100% relative humidity, and so are not condensing. They're not saturated. So that parcel of air it's not full of water. Those parcels of air, as they rise through the atmosphere, they cool down by 10 degrees for every 1,000 meters in height. So if my parcel of air is 18 degrees at sea level, it's rising because it's higher than the temperature around it. By the time it gets to 1,000 meters, it's gone down to 8 degrees, and by the time it's gone down to 2,000, it's gone down to -2. Because it's actually cooler than the surrounding air, which is 0 degrees at that height, it's actually going to be stable there, and so it's not really going to rise much further. That's for dry. Now we need to look at saturated. So saturated adiabatic lapse rate is when the parcel of air has actually reached 100% relative humidity. And that's when saturation is occurring and that condensation occurs and we get clouds forming. So the point for here at which that's going to happen for this parcel of air is going to be 1,000 meters. So once it gets beyond that point, the cooling of that parcel is actually going to go at 7 degrees. So it's actually going to be cooler than the dry diabatic lapse rate. So here my partial of air is 27 degrees, so it's going to rise quite rapidly, but it meets its 100% relative humidity at 1,000 meters. It's gone up by this point at 10 degrees, that dry adiabatic lapse rate. But beyond that, because now it's saturated, it goes down at 7 degrees. So by the 2,000 meters, it's 10. And as it continues, it's still much, much warmer than the surrounding air, so it's continuing to rise. By the time it's 3,000, it's gone down to 3. So there is a reason why it doesn't go, rather than going up at 10 degrees, it goes down at 7 degrees. And that's because as this condensation process is happening, as it's turning the vapor into liquid, it releases latent heat into the atmosphere. So that keeps the atmosphere and that parcel warmer than it should be. So as soon as it starts to saturate, the temperature at which it rises is less than 10 degrees. It's that 7 degrees, and that's a really important distinction we need to know. The last thing to mention here is just when we've got that rising air, when the warmer air is, the parcel of air is warmer than the surrounding air, we get this kind of what we call absolute instability. So you can see here that the air is, once it starts to rise, is much warmer than the surrounding air, and so it continues to rise. It's continuing to rise. However, if the air gets cooler than the surrounding air, that's when we get this stability. So you still get a bit of movement, but you're not getting that kind of massive uplift of air, which was going to create these huge kind of cumulonimbus, cumuliform clouds.